Hello and welcome to this introductory video on combining capacitors. In a previous video we looked at combining resistors both in series and parallel to come up with some effective resistance for that combination. In this video we're going to do the same thing for capacitors. So again we're going to have two choices. We'll have our battery and we'll be connecting it either to capacitors in parallel or in series, which would look like this, for instance. Right, and the game we're going to be playing again is going to be the same sort of thing. Okay, so we know that Q is equal to CV. That's an important relationship, but we're going to have to think about what are the Q's, what are the V's, etc., etc. So we've got a capacitor C1 and C2 and C1 and C2 and some voltage V. And of course what we want to know is what the effective thing is going to be. So what is C effective? We are looking for that. So at that point we're talking about a total charge, which we will call Q, is going to be equal to C effective times V of our battery. But the total charge that's on either one, right, is actually Q1. This one is Q2. This one's Q1 and this one's Q2. Okay. So let's take a look. This time we're going to actually take the parallel case first. Why? Well, because we've got all of this stuff as an equal potential, and therefore we know that we have actually that Q1 is equal to C1 times V, because that's the potential difference across that one. And we also know that Q2 is C2V. And if there's a charge of Q1 on this one and Q2 on that one, then of course Q is Q1 plus Q2. So we have then that C effective in the parallel case rather, so I'll put a little P, is going to be, well, from this expression it should be Q divided by V. Q divided by V. Well, what is Q? It's Q1 plus Q2. Q1 plus Q2 divided by V. And what are those things? Well, it's C1V plus C2V all divided by V. So the V's cancel and we just end up with C1 plus C2 for C effective in the parallel case. Okay, now what about in the series case? That is going to be a bit more difficult. All right, so let's go ahead. Whatever the potential drop across here is, plus here has to be V. So this time we're going to be interested in looking at V, which is Q on C effective. Okay, and so we know what's V1. Well, V1 is Q1 on C1, and V2 is Q2 on C2. Well, what are we going to do with this? We've got, it seems, too many unknowns. But remember that the way that the capacitors work is that on one plate you had sort of minus Q maybe and a Q over here. If I've got Q over here, what am I going to have over here? It's actually linked. I've got the minus Q, they had to come from this plate. And then I'll have Q over here. So Q2 and Q1 have to be the same, because where did the charge on this far side come from? It came from the opposite plate. Okay, it was drawn here by this other charge, which was put there by the battery, and then that drew some charge over there, which left this plate with exactly the same overall net charge. The magnitude of, or the amount of charge, is the same on those plates. So Q1 is actually equal to Q2, which is then equal to Q of the whole thing. So that is just Q on C1, and that is just Q on C2, which is cool. The potential is certainly V1 plus V2. So V is V1 plus V2. So that's wonderful. We can solve this like we did the other one. We'll do C effective is equal to Q on V. But that's Q on V1 plus V2. That in turn is just Q divided by Q on C1 plus Q on C2, which is just 1 on 1 plus C1 plus 1 plus C2, which is 1 plus C1 plus 1 on C2 to the negative 1. And that looks a lot like our formula for resistors. In fact, both of these do, except that they're swapped. So for resistors, when they were in series, they would add, but capacitors in parallel add the capacitances. And resistors added according to this sort of thing when they were in parallel. But for us, this is actually our C effective for series case. Right, so there and there are how we combine our capacitances